Okay. So continuing with the balancing of reciprocating masses, we have seen what is shaking force and shaking couple. So from the above, we have learned that there will be a shaking force and shaking couple, and effect of reciprocating parts is to produce a shaking force and shaking couple. That is what we have explained. Shaking force is due to the horizontal component of the force on the bearing, and shaking couple is due to the couple formed between normal component of the piston on the cylinder walls and the vertical component of the forces acting on the bearing. So the purpose of balancing a reciprocating mass is nothing but to eliminate this shaking force and shaking couples. But the problem is it is impossible to eliminate them completely. So what we do is we opt for an optimum method or a in between method that is called partially balancing or partial balancing. So we only balance the reciprocating masses partially. We cannot completely balance it. We have seen balancing of rotating masses. We can completely balance the rotating masses. We have done the numericals on rotating masses. What we do is we draw force polygon and couple polygon, and we find the magnitude and direction of the balancing mass to be added. So it will be completely balanced. But in reciprocating masses, it is not possible. So how do we partially balance this reciprocating mass? So let us consider a reciprocating masses in a slide diagram mechanism once again to know what is primary and secondary unbalanced forces of reciprocating parts. There will be two unbalanced forces. That is, one is primary and other will be secondary. We will see what are them. So first, just make some parameters, define some parameters of crank accelerator crank mechanism. L is the length of the country rod. R is the radius of the crank. Let theta be the angle of inclination, and let the crank be rotating at an angular speed omega. And along with this, you already know what is n. So and also let m be the mass of the reciprocating parts. So and you already know what is n. N is the ratio of length of the continuing rod to the radius. So n is equal to L by R. So we know in the first module itself we have derived an equation for acceleration due to reciprocating parts. If you remember that acceleration was equal to omega square r into cos theta plus cos 2 theta divided by n. That was the equation for acceleration due to reciprocating parts. Omega square or r omega square, whichever you want to write. So we know by Newton's second law, forces due to reciprocating mass or inertia force due to reciprocating mass will be, let's say, inertia force due to reciprocating masses will be, which is denoted by Fi in the above diagram, that will be equal to m into a, that is mass into acceleration, that will be m into r into omega square times cos theta plus cos 2 theta divided by n, whole divided by n. So if you see the above diagram, you can see that this Fi, that is our inertia force that we found out as mr omega square cos theta plus cos 2 theta whole divided by n, is equal to both this Fr and Fbh, horizontal component of bearing as well as horizontal component of reaction of piston. But we have taken Fr is equal to Fi to cancel out this Fr to make it a balanced condition, and we have left out Fbh. Actually both of this will be equal to Fi. Fr will be equal to Fi and Fbh will be equal to Fi. But we have only considered Fr to cancel out the Fr or the reaction or the force required to accelerate the reciprocating parts, we have equated to Fi, and we have taken out this entire unbalanced force, and we are left with this FBH. But numerically, FBH will be equal to Fi is equal to Fr equal to FBH. And we have taken out this, so this is balanced, and we are left with this unbalanced force. Since now we know what is the magnitude of Fi, we can equate it to FBH, which is our unbalanced force. So Fi equal to FBH, that is horizontal component of force on bearing, that is our unbalanced force, so I am denoting it as Fu, U for unbalanced, that will be equal to mr omega square cos theta. I am expanding that bracket plus mr omega square cos 2 theta whole divided by n. In this, there are two components for unbalanced forces. One is mr omega square cos theta, and another one is mr omega square cos 2 theta whole divided by n. These are the two components, and we call it as primary force, primary unbalanced force, and secondary unbalanced force. So mr omega square cos theta is known as primary unbalanced force, and this is known as secondary unbalanced force, which is mr omega square cos 2 theta, secondary unbalanced force. So these are the two forces that we need to balance, and total unbalanced force will be equal to Fi or Fu, we can call it as equal to we can call primary unbalanced force as Fp, P for primary, and we can call a secondary unbalanced force as Fs. So total unbalanced force will be equal to Fp plus Fs, whereas Fp is equal to mr omega square cos theta, and Fs is equal to mr omega square cos 2 theta by n, where n is the L by R ratio and theta is the angle of inclination of the crank with the line of stroke. Line of stroke is this horizontal. So these are the two components of the unbalanced forces. And what we need to do is, we need to partially balance the reciprocating masses, and what we do is we only partially balance the primary unbalanced force. We do not deal with the secondary unbalanced force, we just partially balance this primary unbalanced force only. That we will see. Okay. So continuing with the balancing of reciprocating masses, we have now seen that horizontal component of the force exerted on the crank bearing as FBH is equal and opposite to inertia force, and we have found out that total unbalanced force Fi is equal to Fu is equal to mr cos theta, and we have found out that this is known as primary unbalanced force and this is known as secondary unbalanced force. Now we should consider these two forces. We can see that primary unbalanced force will be maximum when theta is equal to 0 or 180, because cos theta is maximum at 0 or 180. So, and maximum of that force will be, primary unbalanced force will be mr omega square or m omega square r, because cos theta will be 1 at maximum at 0 and 180 degree. And secondary unbalanced force will be maximum at, because it is cos 2 theta component is there, this cos 2 theta component is there, it is maximum at 0 and 90 it will be maximum, at 180 it will be maximum, and at 360 it will be maximum. So, and the total or the maximum unbalanced force of secondary component will be m omega square r over n. So we see that secondary unbalanced force is maximum, and it's 1 by n times the maximum primary unbalanced force. So 1 by n times means it is less than the primary unbalanced force. So it is secondary unbalanced force is very small compared to the primary unbalanced force. So we normally neglect this force for balancing. Especially at moderate speeds, it is very small in comparison, so we neglect this. So we only balance the primary force or partially balance the primary force. We do not take the unbalanced secondary force, we only balance the primary force. That is why we take partial balancing of primary unbalanced force. We do the numericals based on that concept, that is partial balancing of primary unbalanced force. We only take primary unbalanced force, we do not take that secondary unbalanced force. And how do we partially balance this? Okay, now let's see how the partial balancing of unbalanced primary force of a reciprocating engine is done. So what we normally do is we place a balancing mass B at a radius. B is the balancing mass, and it is placed at a radius B, radius of balancing mass, and it is placed at a radius B diametrically opposite to the crank pin C. That means when the crank is in this direction, we place it directly opposite. So the primary unbalanced force may become, so we know the primary unbalanced force as mr omega square cos theta. So we can consider it as a centrifugal force produced by a rotating mass placed at a crank radius r. That is for ease of solving. So to get this primary unbalanced force, we can consider a mass is rotating at a radius r from the crank. So that will produce an equal mr omega square cos theta in the horizontal direction. So m omega square r will be its magnitude and mr omega square r cos theta will be its horizontal direction. So if you take B, B as the balancing force, this will also generate a centrifugal force BB omega square, and it will have a vertical component and a horizontal component, and the horizontal component will be equal to B omega square cos theta, and the vertical component will be equal to B omega square sin theta. So we know the centrifugal force acting with the balancing mass will be B omega square, and the horizontal component is B omega square cos theta, and the vertical component will be B omega square sin theta. So total primary unbalanced force which is acting is mr omega square cos theta, that is acting in horizontal direction. So it will be balanced if it is equal to the horizontal component of balancing force, which is BB. If these two forces are equal and opposite, then the primary unbalanced force will be balanced. So taking that B omega square cos theta, or we can cut that theta and omega square, so we will get mr is equal to B into B. But the problem is, even if it is balanced, B also has a vertical component perpendicular to the line of stroke, which is this BB sin theta, this one. So it will create another unbalanced force, and the maximum for value of that BB omega square will be mr omega square r. So the which is also the primary unbalanced force along the line of stroke, whereas in the second case the unbalanced force acts in the perpendicular line of stroke. So if we balance the horizontal part of the unbalanced force, horizontal balancing is done, what we will get is a vertical unbalanced force. When we balance the horizontal component of the primary force, we will be left with a vertical unbalanced force, which is BB omega square sin theta. So what we do is a compromise between the both, that is we call it as partial balancing, That is, we will not completely balance the horizontal force. We will only partially balance the horizontal force. That is by taking not total mr omega square is equal to bb omega square cos theta cos theta. But what we will do is we will only take a small fraction of c of the reciprocating masses. That is, we will not take total c. So total m, we will be only taking fraction of reciprocating mass, that is m. That will be c dot m. Normally c is taken as 66. So taking cm is equal to b, or cmr is equal to bb. This is a compromise we take for that vertical unbalanced force that come in. So if you take b is equal to cm, then total unbalanced force along line of stroke of that crankshaft, that is this mr omega square and b square will be there. So if you take total unbalanced force, that will be mr omega square cos theta minus bb omega square cos theta. This is not now balanced because we are only partially balancing it. So b is equal to cmr. So mr omega square cos theta minus cmr omega square cos theta, or we can take 1 minus c mr omega square cos theta. This will be the unbalanced force along the line of stroke. And in the perpendicular unbalanced force will be bb omega square sin theta. This one bb omega square sin theta, but bb is known as cmr. So if I take it, bb is equal to cmr, so it will be cmr omega square sin theta. So these are the two components. One is vertical, other one is horizontal. So we have seen that we will get a horizontal component of the line of stroke component equal to 1 minus c m omega square cos theta, which will be the horizontal component of unbalanced force. And in the perpendicular to the line of stroke, we will get a vertical component that is equal to bb omega square sin theta, or we consider cmr is equal to be, that is we compromise between complete balance and partial balancing. So we only take a fraction of reciprocating masses to be balanced, because if we completely balance the reciprocating masses, then this vertical component will create another unbalanced force. So as a compromise, we only take partial balancing. This is the one of the reasons why we only partially balance the reciprocating mass of primary unbalanced force. If we completely balance it, then this horizontal component will be balanced, but the vertical component will generate another unbalanced force. So in order to eradicate that problem, we only partially balance such that the total unbalanced force remains minimum. We cannot completely balance it. So we make an adjustment such that we only balance a portion of the reciprocating masses, that is C. Normally C is taken as 2 over 3 or 66.66 percentage. 2 by 2/3 of the reciprocating mass are balanced normally, or it will be specified in the numerical to be solved what is C. So as a result, we will be partially balancing, but the effect is that we will not completely eliminate the horizontal, or we will completely eliminate the vertical, but we will be partially balancing the both such that the total vibration remains, or total unbalanced condition remains minimum. So we have got horizontal and vertical components. So the total resultant unbalanced force will be Fu or Fr, we can call it as, will be square root of horizontal square minus, so plus vertical square. So it will be 1 minus c omega square mr cos theta whole square plus C omega square mr sin theta, again whole square. This is nothing but fr is equal to root of fh square plus fv square, that is horizontal component square plus vertical square. So if we can simplify this as fu is equal to total fu, or we can call it as fr. Since it is resultant, it is better to call it as fr, resultant unbalanced force. So we can take out mr and omega square out of this equation because we are squaring them, and we will be left with 1 minus c cos theta square plus c sin theta square. This will be the total resultant unbalanced force of the equation. And if you want to simplify it further, we can take this as 1 minus c square cos square theta, and we can take this as c square, not cos square, sorry, sin square. I think earlier I told sin square theta. So this will be the total resultant unbalanced force. In numericals, this is normally asked to find out the total resultant unbalanced force. This equation is important. So three things you have to remember. One is we only take a fraction of reciprocating masses. Normally it is 2/3, but in numericals it will be specified. So we should take CMR is equal to BB. This is also important for your numericals. Then we should learn this equation. This is the horizontal component along the line of stroke, and this is the vertical component perpendicular to the line of stroke, and the resultant will be square root of those squares, and we should learn this equation. This is also important. And in your numericals, if it is asked to balance, if balancing of revolving masses or rotating masses is also to be done, and m1 is equal to mass of revolving masses, then we should modify this equation. This is only reciprocating masses. M is the mass of reciprocating mass. But if you have to balance the revolving masses also, then we should modify that equation as Cm plus this m1. M1 is the mass of the revolving masses. Cm plus m1 is equal to into R is equal to BB. Normally, in all the numericals, you will be provided with a mass of revolving masses also. So M1 will also be there. So in our numericals, this is also important. Where B is the balancing mass and M is the reciprocating mass and M1 is the revolving mass. You should not interchange or confuse with these three. So this is the procedure or the theory part of the balancing of reciprocating engines. So we will consider a numerical, how to solve a numerical in the next session.